All right, good guys. So today we're going to talk about limits. There are a few different ways of talking about limits, a few different perspectives that you can take on them. And today we're going to focus exclusively on understanding limits from a graphical perspective, basically understanding what a limit is from the perspective of the graph of a function. So there are other ways of understanding limits, and we'll look at some of those. Like they can be understood algebraically, but I think that in order to really understand what a limit is, what it really means, it's best to begin with a graphical perspective. So that's what we're going to do. I'm going to share my screen, and what I'm going to do is switch over to the worksheet, which is your very first worksheet. And as you maybe noticed, the beginning of the worksheet has a bunch of class notes. So I think it's a good idea to take notes on these lessons, as you would in any other class. At the same time, you've also got a copy of these class notes here. And I'm actually going to be working from these class notes as I go through the material. So I have to begin by explaining what a limit is. The truth is there are actually several different kinds of limits. Actually, there's a lot of different kinds of limits. But I'm going to begin by defining three specific kinds of limits, and they're all right here. So there's going to be something called the left-hand limit, a right-hand limit, and then a two-sided limit or a two-handed limit. Those are the three limits that I'm going to begin with: left, right, and two-sided. So here's the definition. So let f of x be a function, like sine of x or x squared, just some function. And let c be a number. So you should imagine that c is just some specific number, like maybe it's 2 or 3 or -8 or something like that. It's just some number, okay? Then the expression limit as x approaches c from the left, this thing right here, this expression that you're seeing right here, this expression is an expression which is the left-hand limit. We pronounce this thing the limit as x approaches c from the left, but what does this expression actually mean? What it means is the value that f approaches as x approaches c from the left, okay? That's the left-hand limit. It's the value that f approaches, the function, that is. It's the value that the function approaches as x approaches c from the left. And I know that that must be a mystery if this is the first time you're seeing it. What does that mean? You'll see what it means in a moment. It's pretty straightforward. Okay, so that's the first limit. The second limit definition that I'm going to make is this one right here. The expression, and you'll notice right here that this expression, this collection of symbols, is exactly the same. It's the same as the one above, except that instead of a little minus above the c, there's a little plus above the c. That's what distinguishes the left-hand limit from the right-hand limit. That's how you tell the difference. So this thing here, this is the right-hand limit, and it's nothing more than the value that f approaches as x approaches c from the right. Okay, that's the right-hand limit. And again, you'll see what that means in a moment. And then finally, this last limit here, this guy here is what we call the two-sided limit, or sometimes the two-handed limit. As you'll notice, there's neither a plus nor a minus above the c in this case, and that indicates that it is a two-sided limit. So this is the value that f approaches as x approaches c from either side, either direction, either the left or the right. And it is critical to understand that this limit is only defined if the left and right hand limits are equal, okay? So only if this guy, the left hand limit, is equal to the right hand limit here, only if those two things are equal is this thing actually defined. If they're not equal, then that two-handed limit is just undefined. So let's see some examples of what these things actually mean. So here I have the graph of some function, and it's obviously a very strange looking function. It's, I guess, a piecewise defined function. There's like all these different pieces, but this is the graph of some crazy function. We're going to use this graph to understand the meaning of these different limit concepts, okay? So one thing I want to make clear before I begin, I want to remind you what these full and empty circles mean. if I asked you, what's the value of this function at 0? Like, what is the value of this function at 0? Hopefully you'd say, oh, well, that means I need to go to 0 on the x-axis and then look and see where the graph is, right, vertically. And that would be right here at 1. So we would say that the value of the function at 0 is 1. But what if I asked you, what's the value of the function at 2? Well, it's a little complicated because if you look at the graph sitting above 2, there's actually kind of these 3 different pieces. And so you might ask yourself, is the value of the function at 2 equal to 3, or is it 4, or is it equal to 5? It's kind of hard to tell because all 3 of those values are sort of sitting above the 2. This is what the full and empty dots are for. They clarify this situation. Because you got a full dot at 4, that means that the value of the function at 2 is 4. The empty dots really just mean that the value of the function at 2 isn't 3 and it isn't 5, but rather it's 4. So that's the significance of the full and empty dots. Well, anyway, let's use this graph to actually evaluate some limits. So let's have a look at this guy right here. This is the limit as x approaches 2 from the left. And I say from the left because, as you can see, you've got this minus sign above the 2. And I claim that the limit as x approaches 2 from the left, this limit right here, I claim it's equal to 3. Now, why is it equal to 3? Because let's remember what the limit as x approaches 2 from the left actually means from the definition. The limit as x approaches 2 from the left simply means the following. You look at 2 and you ask yourself, what value is the function approaching as x gets very close to 2 from the left? So you imagine x getting very close to 2. So here you are, you're getting very close to 2 from the left. You're getting closer and closer. And as that happens, you ask, what happens to the value of the function as you get closer and closer to 2? Well, as you get closer and closer to 2, the value of the function gets closer and closer to 3. I hope you all see that. That's why the limit as x approaches 2 from the left is equal to 3, because as x approaches 2 from the left, the value of the function is approaching 3. So that left-hand limit is equal to 3. All right, well, now let's take a look at the right-hand limit at 2. So limit as x approaches 2 from the right. I claim that's equal to 5. Well, why? Well, let's look at 2. Okay, here it is. And we just ask ourselves, as we approach 2 from the right, so here we are, we're getting closer and closer to 2 from the right, getting closer and closer. As x approaches 2 from the right, what is happening to the value of the function? The value of the function is getting closer and closer to 5, right? And so therefore, the value of the right-hand limit at 2 is 5. Finally, let's consider the two-handed limit, right? So that's the limit as x approaches 2. And as you'll notice, there's neither a plus nor a minus sitting above the 2. That indicates that it's a two-handed limit. Remember, I made this statement a moment ago that the two-handed limit only exists if the left and right-hand limits are equal, if they're the same. But they're not the same in this case, right? The left-hand limit at 2 is 3, and the right-hand limit is 5. Those two numbers are not the same. And so therefore, this thing simply does not exist. It's undefined, okay? But I should mention that, you know, if these two things were the same, like if these two numbers were both, say, equal to 5, then the two-handed limit would just be whatever that common number is. So if, say, the left and right-hand limits were both 5, then the two-handed limit would also just be 5. But in this case, it doesn't have a value because it's undefined. And then one more thing, I sort of mentioned this, f of 2 is equal to 4. This has nothing to do with the limits. This is just saying that the value of the function at 2 is equal to 4. I sort of went over this a moment ago, right? The value of the function at 2 is equal to 4. That's the black dot. Now, you might wonder why I'm even talking about that when this is a discussion about limits, and that's not a limit. Here's the thing. Limits do not care about what is happening at the point. Limits only care about what is happening as you approach the point, as you get very, very close to the point, right? So the left-hand limit at 2, we saw a moment ago, was 3, okay? That's because as you get close to 2, the value of the function is getting close to 3. It doesn't matter what's happening at 2. All that matters is what's happening as you get close to 2. And this is a really critical idea. Limits don't care about, none of these limits here that we just looked at, this one or this one or this one, none of these limits care about what is happening at 2, right? The value of the function at 2 happens to be 4, but this little black dot didn't even enter into our discussion of the value of the limits, right? So limits don't care about what's happening at the point. They only care about what's happening as you get close, as you approach. As a matter of fact, the function doesn't even have to be defined at the point in order for the limits to exist. And we'll see some examples of that in a moment. So let's consider a different point. Let's consider x equals 5, which is right here. You can see something else interesting is happening at 5. So what about the limit as x approaches 5 from the left? So let's see what that is. So we just go over to 5, right? And we sort of ask what's happening. So as x gets closer and closer to 5 from the left, we're getting closer and closer. What's happening to the value of the function? Well, the value of the function is getting closer and closer to 2, right? So the left-hand limit at 5 is indeed equal to 2, okay? What about the right-hand limit? Well, it's also 2, right? I mean, if we go back, if we approach 5 from the right, we're getting closer and closer and closer to 5 from the right. As we're doing that, the value of the function is getting closer and closer to 2 as well. So the right-hand limit is also 2, okay? And therefore, the left and the right-hand limits are both equal to 2, so they're equal to each other, which means that the two-handed limit does exist in this case because the left and right hand limits are equal. And in this case, it's just equal to 2, right? So remember in this previous example at x equals 2, the two-handed limit didn't exist because the left and right hand limits were approaching 2 different values. But over here at 5, the two-handed limit does exist because the left and right hand limits are approaching the same value. Now, what's interesting here is that although the two-handed limit is defined, it's just equal to 2, right? The two-handed limit is defined. However, the function itself is not defined at 5. There is no value because there's simply an empty dot here. The empty dot signifies that, the function's, it's not 2, right? If the value of the function at 5 were 2, it would just be a full dot, or it would just be a corner like this. There wouldn't be this empty circle there. So the function doesn't have a value at 5. The function's undefined at 5, and yet the two-handed limit still exists at 5. And this is, again, getting back to what I've said before, that limits don't care about what's happening at the point. They only care about what's happening as you get close to the point. Yes, the function's undefined at 5, but limits don't care about what's happening at 5. They only care about what's happening as you approach 5. And as you approach 5 from either direction, you're getting closer and closer to 2. Okay? So I hope you're beginning to see what I mean when I say that limits only care about what's happening as you approach the value. Okay, so one more thing about this graph. Obviously, I looked at limits as x approaches 2 from the left and the right, and I looked at limits as x approaches 5 from the left and the right. And clearly from the graph, weird stuff is happening at those 2 points, right? Weird stuff is happening at 2. You can see how the graph is all jagged and made up of these different pieces. And something weird is happening at 5 as well. There's like a hole in the graph, okay? But I want to be clear that you can absolutely talk about limits at points at which nothing interesting is happening at all. For example, we can consider the left and right hand limits at 0. look at x equals 0. Is anything strange happening at 0? I don't think so. The graph is smooth. It's not broken up into pieces. There's not a hole or anything. But we can still talk about limits as x approaches 1. Or excuse me, as x approaches 0. We can still talk about the limits at 0. Right? So I mean, as x approaches 0 from the left, the value of the function is approaching, it's approaching 1. And as x approaches 0 from the right, the value of the function is approaching 1 as well. So the left and right-hand limits are both 1, which means the two-handed limit is equal to 1, right? It exists because the left and right-hand limits are equal to each other. So the two-handed limit exists and it's equal to 1. And it also happens that the value of the function at 0 is also equal to 1. All these ideas coincide. As a matter, like, there's nothing interesting happening at this point. Nothing interesting is happening at 0, but we can still talk about the left and right-hand limits and so on. In practice, though, we will typically ask you questions, at places where weird stuff is happening, right? That's what we'll usually ask you about. Okay, so that's an introduction to limits. Now, that brings us to another concept, continuity. Continuity is a concept that has an everyday meaning, and it has a precise mathematical meaning. And I'm going to tell you about the precise mathematical meaning. So technically, there's a technical definition. So here's the definition of continuity. We say that a function f is continuous at a point c if the limit as x approaches c of that function is equal to f of c. Now, you're probably looking at that and you're like, what is that really saying? What does that mean? I claim that even though this is a pretty abstract definition, I claim that being continuous at a point simply means that the graph of the function has no gaps at that point. That's all it means. Like, if we go back up here, the function is continuous at 0 because there are no gaps in the graph at 0. It's just a nice, smooth, continuous curve. But is the function continuous at 2? No, because there's a big jump, right? Is the function continuous at 5? No, because there's like a hole, there's like a gap. So I claim that being continuous at a point really just means there aren't any breaks in the graph at that point. That's all that it actually means. But if you look again at the definition that I give you for continuity, it's a rather abstract sort of algebraic looking equation, right? We say that a function is continuous at a point c if the limit as x approaches c is equal to the value of the function at c. And one of the big ideas of this lesson, of this particular video, is that you have to understand how this technical, abstract, algebraic definition really does mean simply that there are no gaps in the graph at that point. Okay, that's really what it means. So how can we make that transition? How can we understand that this abstract definition is actually just saying no gaps in the graph? So here's the thing. We have to understand the ways in which this equation can fail, like how it can fail to be true, like what can go wrong to make it so that it doesn't hold, that it's false. Like what can go wrong? What can make this equation break? It turns out there's a lot of things that can go wrong. And in fact, for this equation to actually hold, in order for this equation to be true, a lot of things have to go right. And so what we're going to do is we're just going to unpack that. We're going to try to understand all the things that have to go right in order for this equation to actually hold. And that'll lead us to understand that when this equation is true, there are no gaps in the graph. Okay, so let's begin. Let's try to understand that. So first of all, so what needs to happen? So I claim there are really three things that need to happen in order for this equation to be true. Okay, so first of all, the left-hand side, this guy right here, it is a limit, right? Obviously. And in fact, it's a two-sided limit. It's a two-handed limit because you'll notice that there is no plus or minus above the c. So that's a two-handed limit. And remember what I said about two-handed limits. They're only defined if the left and right hand limits match, if they agree, if they're equal. So first of all, this expression needs to be defined. It might not be, right? In order for this equation to be true, this overall equation to be true, this expression here has to be defined. Okay, so that's one thing that has to go right in order for this equation to be true. You can't have a true equation involving undefined components or undefined expressions. So in order for this equation to be true, this guy here has to be defined. So that's one thing that has to go right in order for this equation to be true. Let's look at the right-hand side of this equation, f of c. What does that mean? That's the value of the function at c, right? That expression can also be undefined. Like it's possible that that expression is simply undefined. It's possible that the function is just undefined at c. Maybe, for example, putting c into the function gives you a 0 in a denominator. That's undefined, right? Or maybe the graph of the function looks something like this. Remember this graph right here? Remember at x equals 5? This function has no value at 5. And so if c were equal to 5, well, the function, the expression f of c would be undefined because the function is undefined at 5. So just like this guy right here, the left-hand side of the equation, it's completely possible that this guy is just undefined. That's something that can go wrong. So again, in order for this whole equation to be true, this expression must be defined. The function must be defined at the point, okay? So that's the second thing that needs to go right in order for this equation to be true. The function needs to be defined at the point, okay? But that's still not enough, because even if this expression here is defined, and even if this expression here is also defined, they need to be equal to each other, right? They need to be the same number. And that's the third thing that needs to go right in order for this equation to be true. Okay, and beyond this expression being defined and this expression being defined, they have to actually be the same number, right? Of course. So those are the three things that need to happen in order for this equation to be true. In other words, those are the three things that need to happen in order for the function to be continuous at the point. The two-sided limit must exist. The value of the function at the point must exist. And finally, those two numbers must be equal to each other. Okay, and if you really think about that, if those three things hold, that means that the function has no gaps. It has no jumps, no breaks in the graph. It means that the function has no gaps. Okay, so we're going to look through some examples and really see why that is. So I've sort of numbered these three things, right, that hold. So, property 1, like the first thing that needs to happen is that this guy is defined. Okay, property 2, the second thing that needs to hold is that this guy needs to be defined. And property 3 is that even if both sides are defined, they actually need to be equal to each other. So let's kind of look at what happens in the following examples. So here, I've got a graph of some mystery function, just some unknown function. And as you can see, there's a gap in the graph right here. Okay, so at C, you can see that there's a gap in the graph, which means we should expect that this thing isn't continuous, right? Just sort of intuitively, we can see that there's a hole in the graph, which means that this thing shouldn't be continuous. But let's see how that comes out from the technical definition. Okay, I claim that because there's a gap here, this equation is going to fail somehow. Something is going to go wrong. Okay, so what's going to go wrong? Well, let's think. Okay, let's just look at the three properties, 1, 2, and 3, and see which of them fails. Okay, so the first property is that this guy is defined. Is that thing defined, the two-handed limit? Is the two-handed limit defined at C? Well, what needs to happen for the two-handed limit to be defined? The left and right-hand limits must be equal, right? They have to be going to the same number. From the left and the right have to be going to the same number. And is that true here? Yeah. Yeah, as you approach from the left and the right, they're both going to the same value. So the two-handed limit does exist. Okay, so this guy does exist in that case. All right, what's the second thing we need to check? Well, this guy has to be defined. That's the value of the function at the point. Is the function defined at C? Does the function have a value at C? Actually, no, it doesn't. That's the meaning of this empty circle here, right? That's the meaning of this empty circle. The function doesn't have a value at C, which means the right-hand side of this equation is undefined, which means automatically this equation has to fail. Okay, this equation fails, which means by definition, the function is not continuous as we expected. Okay, so as we're going to see, anytime there's a gap of some kind in the graph, something about this equation is going to break. All right. Yeah, so property 1 was true, so that's why I wrote 1 holds, right? Property 1 is holding here, but property 2 failed, right? And then I say that 3 fails automatically because, like, remember the third property is that even if both halves of this equation are defined, they have to be equal to each other. Well, if one of them is undefined, then that like automatically is going to fail, right? If one of them's undefined, they automatically can't be equal to each other. That doesn't make any sense. So that's why I say that property 3 sort of fails automatically. Okay, let's look at this picture here. So here's a different graph, right? We got this point C, and we can tell that surely this function's not continuous at that point, right? There's no way it's continuous. Look at the gaps in the graph, right? You can see these gaps. So we should expect something to go wrong with this equation, right? But what exactly is going wrong? So let's go through the 3 things that need to happen in order for this equation to be true. So as I said, the first half of the equation must be defined, okay? And that's the two-sided limit. Well, is it defined in this case? Does the two-handed limit exist in this case? No. The two-handed limit only exists when the left and right-hand limits are approaching the same number, and you can see that they're not here. One side on the left is going to whatever that value is, and then on the right, the function is approaching some other value. So the left and right-hand limits aren't the same, which means the two-handed limit doesn't exist. Okay, so since this side of the equation is just straight up undefined, the equation can't possibly be true, which means the function's not continuous at C as we expected. But let's just look at property 2. I claim property 2 actually holds, right? The second half of the equation is defined. Is that true here? Is the second half of the equation defined? Is the value defined at the point? Yeah. The value of the function at C is, whatever the y coordinate of this dot is here, right? Because we've got this full dot, the function is defined at C, okay? All right, let's look at this guy right here. So again, you can see some kind of a gap. So we should expect, this thing's obviously not continuous, right? So we should expect something to go wrong with this equation. Well, what goes wrong? Well, let's think. Say, okay, so is this thing defined? Right? Is the two-handed limit defined? I think so, because the left and right-hand limits are the same number, right? They both go to the same value. So, okay, so that's defined. Great. This guy here is defined. Is this guy defined? That's the value of the function at the point. Is the function defined at the point? Yeah, the function's defined at C. It's whatever this value is right there. Okay, so both this guy and this guy, they're both defined, but remember there's a third thing that needs to happen. Even if they're both defined, they need to be equal to each other. And are they equal to each other? No. The two-handed limit is whatever this y value is. That's what you're getting as you approach C, right? That's the value of the function as you approach C, this value right here. But the value of the function at C, at the point, is this guy up here. And so they're different. So both the two-handed limit and the value of the function exist, but they're not equal to each other, right? The two-handed limit is whatever this guy is, but the value of the function at C is whatever this guy is. They're not the same. So 3 fails, okay? Even though, both halves of this equation are defined, they're not equal to each other, so this guy fails. Finally, we move on to here, okay? Do you see any gaps in the graph here? I don't see any gaps in the graph. So we should expect that this function is actually continuous. In other words, we should expect that this equation is actually true in this case, okay? Well, let's check. Let's check the 3 things. So is this guy defined? That's the two-handed limit. Well, the two-handed limit is defined when the left and the right-hand sides go to the same number, and they do in this case. So the two-handed limit is defined. Great. So this side here is defined. Now, what about f of c? Is the function defined at c? Yeah, right? I mean, what the value of the function at c is whatever this number is right here. There's no empty dot signifying that it lacks a value or anything like that. So yeah, the function has a value at c. It's whatever this number is right here. Okay, and so, so this guy exists, and this guy exists. And then finally, are they the same number? Yes, they are, right? The two-handed limit is whatever this number is right here. And the value of the function at c is that number right there, okay? And so in addition to both sides being defined, they are in fact equal to each other, which means that yes, this equation is actually true, which means as we expected, yeah, this function is actually continuous at c. So as I said, being continuous at a point simply means no gaps, no breaks in the graph. That's all that it means. But the technical mathematical definition is this, abstract definition right here. And you really need to be able to see how it is that, when this equation breaks down, when it's false, there's some kind of a gap in the graph. And when this equation is true, that means that there isn't a gap in the graph, okay? All right, so I think that is actually the end of today's lesson. The worksheet has a whole bunch of exercises here for you to practice evaluating limits. We give many of the answers to the problems, but not all of them, because we want you to sort of think carefully and not just sort of blindly, write the answers down. I'll go over some of the blank answers tomorrow at the beginning of class. If there's one that's really, that you're really stuck on, just send me an email. So there is a little bit more in the worksheet that we sort of walk you through here. It's just a little bit of reading, but I think it's pretty self-explanatory. I think you should be able to get through it on your own. And then finally, I do want to warn you, exercises 4 and 5 tend to be pretty challenging. Okay, they tend to be pretty challenging. When students first encounter these exercises, they really tend to get kind of lost. As you'll see, we're looking for a graph which satisfies all these different properties, and the first time that students do it, they're kind of lost. But I'm going to go over one of these exercises tomorrow at the beginning of class. So do your best, and then watch the video and see if you figured it out. But that is, and answers are in the back. Okay, most of them. Okay, or many of them. So make sure you're checking your answers as you go along, right, and making corrections. That's really important. So okay, see you next time.